If you want to master your NMR problem solving skills, then you are in the right place. Welcome to the NMR Challenges series, where each video presents a new NMR spectroscopy problem from beginner to advanced level. Here, we systematically analyze 1H and 13C NMR along with 2D techniques such as COSY, NOSY, HSQC, and HMPC, depending upon the problem, to uncover organic structures step by step. So let's get started. We have taken this NMR problem from Pavia Spectroscopy book, 4th edition. Page number is 223, problem is 12. We have to determine the structure of organic compound having molecular formula C10H12O2 from the given spectral data such as IR value, DEPT 135, DEPT 19, and proton NMR. By the end of this video, you will understand how to calculate the index of hydrogen deficiency, how to interpret 1H and 13C spectra, how to analyze advanced spectra such as DEPT 90 and DEPT 135, and how to integrate all the data logically to identify the correct structure of the organic compound. I follow a specific step-by-step process for determining the structure of organic compound, and I would like to recommend you to follow the same approach. First, look the IR value or IR spectra to determine the functional group present in the molecule. Then calculate the index of hydrogen deficiency, which gives you information about number of pi bonds or rings, or it could be both, present in the molecule. According to my experience, if index of hydrogen deficiency equal to 5 or more than 5, then we can say that this compound contain one benzene ring. Then look at the 13C NMR. Normal 13C NMR gives signal for all sorts of carbon, means all types of carbon signals you will see. Then look at the 90, DEPT 90 NMR, which gives you how many types of CH methane carbons are present in the molecule. After that, look DEPT 135. In DEPT 135, only those carbons showing the signals which possess the hydrogens. So it means the signals for quaternary carbon or carbonyl carbon will be absent. Therefore, you can easily conclude that which signals belongs to the quaternary carbon by comparing with the normal 13C carbon spectra. And remember that methane CH or methyl CH3 peaks coming in the positive phase, means in the upward direction. Methylene signals comes in the negative phase, it means in the downward direction. And at the end, look 1H NMR. The number of signals in the 1H NMR is equal to how many types of protons are present. If you are seeing that number of hydrogen signals are half of the total number of protons present in the molecules, then it means your molecule have symmetry. And same in the carbon NMR also. If you see the carbon signals, let's say 5 carbon signals and there are 10 carbons, it means the molecule has symmetry. Okay, the splitting patterns in 1H NMR following n+1 rule, then you can get the information about the neighboring protons, and eventually you will understand which type of functional group or group present in the molecule. Substitution patterns in case of benzene ring you can determine by the splitting pattern. Chemical shift values is very important to remember because it will gives you information about the shielding or deshielding of the protons. I would like to recommend you to remember few chemical shift values. For example, if alpha hydrogen is connected to the ketone or ester, then it is coming in between 2 to 3 ppm. If the carbon is connected to the electronegative atom such as oxygen, nitrogen or fluorine, then the signal will come around 3 to 4.5 ppm. If it is connected to the bromo or chloro, then it comes between 2 to 3 ppm. The signals for alcohols or amines is variable, so you can see from aliphatic regions up to the 5 ppm. Phenol signals usually comes around 5 ppm. Now look at the alkenes, which comes from 5 to 7 ppm. For aromatic compounds, the signals comes from 6.5 ppm to 8.5 ppm. Aldehydes protons gives characteristic signals between 9 to 10 ppm, and similarly carboxylic acid signals will come from 11 to 12 ppm, always beyond the 10 ppm. Okay, if you remember these values, then you can easily figure out the presence of the functional group in your molecule. So first we will see the IR value, which is 1711 per centimeter. This value indicates that the compound could have ketone, aldehyde or ester, conjugated ester. Yeah, because usually ester comes around 1735, but if it is in conjugation, then it can decrease further, but we don't know which one is actually present in the molecule. So it's better to check carbon NMR. In the carbon NMR, if you see, there is a peak
around 207. This 207 indicates that the compound containing carbonyl group of the ketone or aldehyde. Now look at the 1H NMR. In the 1H NMR, there is no signal around 9 ppm, right? Therefore, this compound does not have aldehyde, and it is also, you can rule out the presence of the ester group. So what is present in the molecule? The molecule have keto group. Now we are going to calculate the index of hydrogen deficiency. The formula is 2C plus 2 plus number of nitrogen minus number of hydrogens minus halogens divided by 2. So 2 multiplied by 10 plus 2 plus 0 minus 12 minus 0 divided by 2 equal to, so the molecule has 5 degree of unsaturation. It means that this molecule has one benzene ring, and one benzene ring is attributed for 4 degree of unsaturation, and 1 degree of unsaturation you can assign to the keto group. So now we have balanced the degree of unsaturation with benzene ring and keto group. Now look at the normal 13C NMR. So there are 1, 2, 3, 4, 5, 6, 7, 8 signals, and we know that this signal belongs to the keto group. Now look at the DEPT 90 NMR. In DEPT 90 NMR, this peak, which is at 29 ppm, is missing, which indicates that this peak maybe belongs to the methyl group, right? Because in DEPT 90 NMR, you are going to see only CH signal, only methane carbons. For 50, it is absent as well. For 55, this is also absent. And 140, this one is present. This peak number 5 is also absent. This peak is present. And then this peak and these peaks are absent. So this indicates that the compound have only two CH, two types of methane carbon, right? And this belongs to the benzene ring, right? These values belongs to the benzene ring. It means that the benzene ring has two quaternary carbon, and this one which is 159, this one, and 126, right? So the benzene has two substitution. This is very clear from the carbon NMR. The benzene has one substitution, okay, and another substitution, and we don't know the position of the substitution, okay, but we know that this benzene ring has two substitution. That's why two signals are missing from the benzene in the DEPT 90 NMR. Now look at the DEPT 135. In DEPT 135, this is positive signal. Okay, now it is positive. It means this is belongs to the methyl group for sure, because in the positive direction you see the signals for methyl and CH, right? And in the negative you will see the signals for CH2. So this signal is belongs to the CH2, and it looks like that it is deshielded. So it looks like that it could be attached to the oxygen or CH2, but we are not sure. Now look at 55 signal. This signal is in the positive phase. So this positive phase, and at the same time it is around 55 ppm. So it means it is attached to the oxygen for sure. So there is a methyl, another methyl, yes, which is attached to the oxygen. So, and the molecule has two oxygen only, and we have already assigned one oxygen to the ketone and one oxygen we are assigning to this one. So it means the molecule does not have OCH2. Okay, now let's move forward. This peak number 114 is in the positive, of course, and 126 is missing here because there is no hydrogen. 130, of course, there will be a peak, and 159 is missing, as we know that it is quaternary carbon, and this is keto, it is also missing. Okay, so what information we are getting from all these carbon NMRs is that the benzene is disubstituted, right? Because two quaternary carbons are there, so benzene is disubstituted. Second information is that the compound has OCH3. It also have CH2 and methyl. This one, yes, methyl group. Now let's move to the proton NMR. In the proton NMR, there are 1, 2, 3, 4, 5. 5 types of signals. It means there are 5 signals, means 5 types of protons are there. Now look at the signal around 2 ppm. Let's say this is somewhere around 2 ppm. It is singlet and it corresponds to 3 hydrogens. This means that there is no neighboring hydrogens, and this could be belongs to the methyl, as we already know that from the carbon NMR, but this methyl is attached to the keto group. That's why it is going to the 2 ppm, and we have already discussed in the chemical shift value. Now look at the signal B, which is around 3.6 ppm, and it is also singlet. This is corresponding to the 2 hydrogen. Now the neighboring hydrogen 0, and this CH2 indicates that there is a presence of methylene carbon. But now this is very this also indicates that it could attach to the oxygen, right? Because it is coming around 3.6 ppm. But from the carbon NMR, we have seen that methoxy is present. So therefore, we can rule out the presence of this one. So what does it mean? Why it is going in the negative field? I mean, why it is going to the quite deshielded region? It means this CH2 can attach to the two groups which are electronegative. Yeah, you can say that it could be attached to the electronegative carbon. Okay, so we will see what are those electronegative carbon when we will be close to drive the structure of the organic compound. Now signal C is also around 4 ppm, and this is also singlet, and it corresponds to 3 hydrogen. So neighboring hydrogen 0, singlet means neighboring hydrogen 0, and C3H means it is attached to, it belongs to the methyl, and this methyl is attached to oxygen. That's why it is going in the 4 ppm. Now look at the aromatic region, and this aromatic region is very important because you are seeing doublet, yes, somewhere around 7 ppm, let's say 7 ppm, or it's around, let's say another one is around 4 ppm. Okay, this value doesn't matter, just I cannot see what is the value here. So this is doublet, and this corresponds to 2 hydrogen. This is also doublet, correspond to the 2 hydrogen. This pattern indicates that the benzene ring is disubstituted. Okay, this we have already confirmed from the carbon NMR, but now we know the substitution pattern. This is para disubstituted. That's why you are seeing the doublet, two doublets, right? Two doublets, because when the benzene ring is para substituted like this, then it has plane of symmetry. Let's say this is X group, this is Y group. It has plane of symmetry. This one, this hydrogen will show doublet, this hydrogen will show another doublet, and chemical shift value will be different. So this has two types of the hydrogen. Okay, so let's write all the information which we got from all the spectral data. So first we understand that the compound has one benzene ring which is para substituted. Okay, and the compound has O CH3 group. It also has CH2. It also has CO CH3, right?
Okay, now we have all pieces of information. It is time to put them together. This step requires careful logical thinking, and we must consider all the possible structures and identify the one that is fully consistent with the molecular formula, index of hydrogen deficiency, and all the spectral data. So let's do it together.
So let's see all the possible structure for this compound. So the first one, it could be like this, that OCH3 is here, and then this CH2 is here, and which is connected to the keto, and then CH3. This is the only possible structure. If it is the correct structure, then it should fit to the 1H NMR, right? Let's do the back testing. So this one is going to show signal A, this one is going to show signal B, and now you can see that why it is coming around 3.5 ppm, because it is connected to sp2 carbon here, and here is also electronegative carbon, which is ketone carbon, right? This is also withdrawing the electron density. That's why it is going 3.5, and it seems that it is attached to the oxygen, right? But it was not the case. And now look at the signal C. Signal C is coming from this methoxy hydrogen, and one of them is D, and another one is E. We cannot precisely say which one is D and which one is E. It doesn't matter. Now let's look at the molecular formula. So molecular formula will be C, 6 carbon from the benzene ring, 7, 8, 9, 10. yes, 10. Hydrogens 3, 2, 5, 8, 9, 10, 11, 12, yes. And how many oxygen? 2 oxygen. So it is consistent with the molecular formula 1H NMR. Now let's look at the 13C NMR. So in 13C NMR, there is a signal for keto group. So this one is 207. This methyl was 29 ppm, right? This CH2 was at 50, and this one, and here one of them was quaternary carbon. So probably it is attached to the oxygen, so it could be 159, and this could be 126, and then you have 114 and 126. So one of them is 130, right? This is also consistent with the carbon NMR, and hence we can say that the correct structure for the given problem is 4-methoxy phenyl acetone. This is the name of this molecule.
So that's all for today. I hope this video helped to strengthen your NMR skills. Keep practicing because mastery comes with consistency. And I will see you in the next video with the another exciting NMR challenge. Make sure to subscribe so you don't miss it. Till then, take care. Bye bye.